Hello, my name is Ryan Pearman. I am the Director of Modeling at D2S, and I'm here to talk today about why people are talking about doing mask modeling on today's latest mask processes. Or simply put, why is it that the shapes we tape out are not the shapes that end up printing on the mask? Well, one can ask if this has always been happening, and the answer is it's actually true, but why didn't we care about it? Well, the reason we didn't care about it before today is because the eBeam writer tools and the mask process engineers did a very good job classifying where mask process errors exist and segmenting them and avoiding them. We can look at the mask process really on three different length scales. On a 10 nanometer length scale, we have something called forward scattering. On a 10 micron length scale, we have something called back scattering. And on a 1 millimeter length scale, we have something called etch effects, as well as eBeam fogging effects. Now, I'll explain all these effects later, but suffice it to say that all of these effects have been known and dealt with. But why are we revisiting it today? The reason we're revisiting it today is because the error budget on wafer is so much smaller than it was before. With the advent of double patterning technologies and EUV technologies and very, very small main features, the CD control limits on the wafer fab, as well as the overlay limits on the fab, are really down to sub-nanometer levels. There just is no room for error anymore anywhere in the wafer processing flow, and the mask processing flow is one place we can enhance both the CD uniformity as well as the direct CD itself. So let's talk today a little bit about how well we do with printing 1D features. So if we look at this plot here, what this is a plot of is a plot of what is actually printed on a mask minus what the CAD designer has taped into the mask. So for large features, on the order of 200 nanometers and above, what you want is generally what you get. But as you get progressively smaller, down between 100, even 60 nanometers, you can get upwards of 10 nanometers of difference between what you printed and what you desired. So what that means is sub-resolution assist features, which fall in this range in particular, or even some main features for tight pitch 193 layers, or any EUV layer for that matter, will print smaller than is expected than the larger lines. What that means is there's going to be a bias on wafer between small lines and large lines that an OPC model will have a very large difficulty figuring out. In the end, you'll end up with a very poor OPC model, and in the end, you'll end up with a yield loss at the end of line. For 2D features, it gets even more interesting. If you try to print a contact that is small, there ends up with a significant amount of corner rounding effects. As a result, the open area for the smaller contacts really drops. And because 193 layers in particular depend exclusively on open area for the size of the print, you'll end up with, again, a print bias between a large contact and a small contact, which will yield to both resist patterning as well as etch patterning yield losses at the end of the line. So as a result, for 20 nanometer nodes or below, either from a 1D perspective or from a 2D perspective, the mask features that are printed really are not good enough for high quality yield. Okay. So to start uncovering why the current methodology needs improvement, let's focus on the physics and the steps in the mask making process. And these are located right down here. Now it should be noted that this is not going to be a treatise on the mask process flows, but rather the key steps that really define the pattern that you observe at the end of the mask processing. So first you get the mask ready. You have your blank and you put some resist on top. Now what's interesting is that the choice of resist that you choose here will greatly impact the trends that you see that I discussed earlier in this talk. And interestingly enough, the increased resolution requirements, because we're printing small features, have actually driven changes in the resist, which makes the approximation of ignoring forward scattering a very bad approximation. And that is most likely the direct contributor to the 1D linear effect we just talked about. The data then comes in. The data comes into the eBeam tool in the form of shots, which are processed at the mask data prep stage. We've taken the output of the OPC or the CAD data, and we've broken it apart smartly into either rectangles or right triangles, depending upon the pattern shape. Now, it's well understood that these algorithms which change the OPC data into a set of shots, can adversely impact or improve the CD uniformity. But what's not really well understood is the choice of shots used can also impact the CD itself. So once you have these shots, they are then sent to a VSB writer tool, typically the 50K EV eBeam tool in most of the mask shops today. And this eBeam tool transfers these shots into the mask stack, into the resist. This is typically what's thought of as the CD defining step, but in reality, this step simply sets up what we call a latent image in the resist. No pattern is yet visible on the mask, but the pattern is visible chemically inside the resist. We then go to further resist processing, where some very neat chemistry forms the pattern in the resist layer. And there are a lot of steps that go on here, which we don't have time to discuss in this session, but in the end, the result are resist lines, which protect the underlying mask, and resist spaces, which expose the underlying mask. That will form the basis of the final mask pattern. Finally, we then go to the etch process, where some more neat chemistry then transfers the pattern set up in the resist to the actual physical mask, where you etch the chrome or the glass or the absorber, depending upon the type of mask that you're making, where the resist isn't present. Then you remove the resist, do some more clean steps, mount your pellicle, inspect your reticle, and then ship your reticle to your final customer. Okay, so now that we've talked a little bit about the physics that's involved in the mask making process, let's go ahead and relate that back to the 4 things we discussed before in the sort of the standard mask modeling process. Of those 4, forward scattering, backward scattering, etch bias correction, and fogging correction, only one of those has nothing to do with resist, and that's the loading effect correction. That's beyond the scope of what we're going to discuss today. We'll get into the non-idealities of loading correction in a future session. So of those 3 remaining that dealing with resist, let's talk about fogging first. What happens with fogging is electrons from this eBeam tool will reflect off the top of the resist itself and go back into the vacuum of the tool. And then, for lack of a better word, these things scatter around off of the sides of the tool and many other things and essentially form a fog of electrons above the resist. This thing is very well characterized, very easy to model via a simple Gaussian density effect, and is very accurate in describing the effect of very long-range backscattered electrons. As a matter of fact, the people in the wafer side see this kind of effect too. It's called flare, and it's modeled in exactly the same way. So what's left to explain some of these non-idealities, these non-linearities, is really then backscatter and forward scatter. And to under the scattering processes, because that happens inside the resist itself, let's take a look at what happens to electrons once they enter the resist and the mask stack. So let's segue then into a discussion of the eBeam writing step itself. The VSB writer takes a beam of electrons and passes it through a shaped or typically rectangular aperture. These electrons are then projected down onto the resist. Now, in particular, some of this projection process involves a focus, but due to an electron-electron interaction, this focus is going to be of non-zero size and results in a beam blur, which is typically called a Coulomb blur. Mathematically, what happens is this ends up blurring the edges of a VSB shot even before it hits the resist, and the magnitude of such a blur is on the order of 10 nanometers. That blurred shot then impacts the top of a resist material. These electrons are typically traveling mostly straight down. They have a lot of energy, so they penetrate very deep in the material, through the resist, through the mask stack, and well into the quartz below. Inside these materials, they interact with atoms and molecules, and such interaction events we typically call scattering. Now, the scattering events can take place, consist of many things. Electrons can collide, they'll change direction, but by doing so, they can impart energy in the form of vibrational or thermal energy, as well as electronic changes, electronic energy, into the individual molecules. The electron can also be captured by a molecule, it could be trapped, and it can create a local charge, such that additional electrons that pass through the vicinity can have their trajectories altered by the presence of this charge. Electrons can actually eject other electrons by either of the 2 methods above, whether by scattering or actual capture. And these so-called secondary electrons, these Auger electrons, can have an arbitrary trajectory but otherwise they continue and behave similarly to any other electron trajectory that we're following. Lastly, again through either collisions or capture, electrons can create chemical changes in the material. And in modern resists, it's these chemical changes which are responsible for the pattern that is ultimately delivered into the resist. Additionally, when one has layer-to-layer interfaces, there's many more reflection events. Inside the resist, it's typically not considered a fogging event, but what will end up happening is you get trajectories that go off this way, and those end up with the so-called backscattered electrons. And in the end, what you can find is that electrons can end up tens of microns away from where they started from due to these interfacial or low in the quartz scattering events that result in what we call backscatter. As an aside, if you look at an EUV mask, the presence of this multilayer induces many, many more interfaces, which gives many, many more trajectory changes, which is why there is a much broader blur of electrons, and it actually gives rise to the EUV mid-range effect, precisely due to these multilayer effects. And in fact, if you take a look at where the electrons end up and the total energy distributed, most of the energy ends up, about 2/3, ends up in what we call the short range effect. They end up about 0 to 100 nanometers away from where it started from. This regime here is where the idea of a forward scattering really arises. These electrons are considered forward. They're typically the ones that have come straight down, and they're typically blurred like this. That's why they're called forward. But those electrons that have scattered off of other molecules and have trajectories that go way off to 10 microns, it turns out that about a third of the energy, the other third of the energy, ends up at about 10 microns away. Now, of course, there's a and then, by the way, that's where the consideration of backscatter electrons come from. Now, of course, the electron energy is continuous amongst this range, but if you look at these two length scales, a peak of energy at 10 nanometers, a peak of energy at 10 microns, that's where this concept of forward and backscattering really comes from. So we've described briefly where the mask nonlinearities come from. We described briefly some of the key mask processing steps in the patterning process, how they connect to the various corrections that are done on the tool, and why these corrections are beginning to break down. So in the future editions of FineLine, we'll get really into the meat of these simulations. We'll discuss what's going on in the neat chemistry of the resist and the etches. We'll talk about some of the computational trade-offs that have to be made for computing the scattering processes. What we'll end up with is how we end up with the resist standard 1G model. Thanks for your attention.